Tell all the hunters lay on their guns. Oh, hey everybody. Hey, it's Joe Exotic here. Hey, Mr. O'Sullivan couldn't be here today, so he wanted me to just sit in, and I just want to show everybody that a lot of people think they've been watching my show and stuff. They think I'm a moron, but I just want y'all to know that Joe Exotic can do some calculus. So here we go. We're going to dive in. We're going to work on a problem from 2007 exam. And we've been talking about related rates. And so we're going to look at problem number 5. So let's just take a looky-loo, shall we? All right. Well, they give us a table. And we got a volume of a spherical hot air balloon expands as the air inside the balloon is heated. Radius of the balloon in feet is modeled by a twice differentiable function r times t. T is measured in minutes. The open interval 0 to 12, the graph R is concave down. I'm going to highlight that little piece of information right there because I think that might be a little important. So, all right, said the graph R is concave down. All right. Table above gives selected values of the rate of change R prime at T of the radius of the balloon over the time interval, closed interval 0 to 12. Radius of the balloon is 30 feet when T equals 5. I think that also might be a little bit important. So I'm going to highlight that right there. Radius of the balloon, 30 feet, T equals 5. Note, the volume of a sphere of a radius R is given by the equation V equals 4/3 pi R cubed. Well, shoot, anybody knows the volume of a sphere, radius R, is given by that formula. I bet even Carol Baskin knows that formula. All right, what do we got to do? Part A, we got to estimate the radius of the balloon when T equals 5.4 using the tangent line approximation at T equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. I hate it when they always ask you to give a reason for your answer. All right. Part B, find the rate of change of the volume of the balloon with respect to time when T equals 5. Indicate units of measure. Well, that right there, my friends, that's going to be important. I'm going to highlight that so I don't miss an easy unit point right there. Part C, use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate the definite integral 0 to 12 r prime at t dt. Respect that differential now. Using correct units, oh my gosh, units again. Using correct units, explain the meaning of the definite integral 0 to 12 r prime at t dt in terms of the radius of the balloon. Okay, and part D, Pete's sake, finally all done. Part D, is your approximation in part C greater than or less than the definite integral 0 to 12 r prime at t dt? Give a reason for your answer. There we go again. Give a reason for your answer. All right, well, let's do this because I got things to do. I got tigers to feed and stuff to do, and I don't want to be sitting around having to do more calculus than I have to, although I do love calculus. Not a lot of people know that. All right, so let's look at part A. Estimate the radius of the balloon when T equals 5.4 using the tangent line approximation at T equals 5. Well, first thing we got to do is come up with that tangent line approximation. Never done that before, have we? Only about 1,000,000 times. All right, tangent line approximation. Well, I got to have a point of tangency, and I'm going to always start out with, I always write my tangent line approximation. What do I start with? That's right, point slope form of line. All right, I know you know that. Even Carol Baskin knows that. All right, hang on. Stupid notability. All right, see. So, starting out, point slope form. I'm just going to use y's and x's. They're not going to ding you for using y's and x's. So I'm going to go y minus y1 equals my slope times x minus x1. There it is, point slope form of a linear line. Okay. So now I got to drop in my point of tangency. Well, my point of tangency is going to be when t equals 5. There's my value there I'm going to put in. And then what's my radius when t equals 5? Well, that's going to be 30 feet. I knew I needed to underline that and highlight that. So there it is. So I'm dropping that in. Just put that point right there to remind me. That's my t value. And then my r is going to be 30. So I'm plugging that in. So y minus 30 is equal to, I'm going to figure out slope in just a second. Don't get all your knickers in a knot. X minus 5. Okay, now I got to figure out, well, this is really giving me a radius. That's my equation. It's going to estimate the radius. So I'm really looking for r prime at 5. That's going to be my m. So I'm going to go up here. Darn it, I hope they gave that to me somewhere. But there it is. It's in the table right there. R prime, there's 5. 2.0 is my number. There we go, 2.0. So I'm going to plug that in for m. So I got y minus 30 is equal to 2.0 times x minus 5. Okay, I know I'm going to get people complaining, just jawing at me. That's not really x. All right, I'll change it. Jeez, my goodness. Call that t. There. You happy? I'm going to leave that y alone, though. I know some of you are going to be arguing, well, that ought to be r. Well, no, it shouldn't be r. We're using the tangent line approximation. It's a separate type function. All right. Now, there's my tangent line approximation. Now I got to do one more thing. I wrote that. Now I got to use that to give me an approximation of the radius when t equals 5. Well, actually, I'm sorry. When t equals 5.4, I was like, well, that's not going to do much because that's going to be 5 minus 5. It's not going to be 30. All right. So I'm going to put in 5.4 minus 5 times 2.0 equals, now I do have to do one more thing. I got to add this 30 to the other side of the equation. So now I have a numeric answer, y equals 2.0 times a quantity 5.4 minus 5 plus 30. We'll put that plus 30 right there. And I'm just going to let some poor AP reader figure out if that's the correct answer or not, because that right there is a numeric answer. All right. I think I got all part A. Oh, no, I did. Good thing I went back and I read it. Yep, I bet Carol Baskin wouldn't have gone back and read it again. Is your estimate greater than or less than the true value? Give a reason for your answer. Well, let's see. If I look at R and they're telling me R is concave down, well, and it don't matter nothing neither. If R is concave down, it's either going to look like this or it's going to look like that. It could be concave down decreasing, concave down increasing. They just tell me it's concave down. Now, if I draw here a tangent line on top of that, don't matter where I draw it, just on top, it's going to be up above my actual function. So my function is concave down, and I'm doing a tangent line approximation. My tangent line approximation is going to be, my estimate is going to be greater than my actual value. Okay, so there we go. I'm going to add that to it, and I'm going to say the approximation is greater than the actual value. Well, and that actual value, I guess, would be R at 5.4, whatever that actually is. All right? All right. Now we're moving on to part B. Picking up some steam. Find the rate of change. Rate of change, that strikes, that kind of rings a bell a little bit. I think I heard that one time. Find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate units of measure. Well, shoot. I wonder what rate of change of the volume of the balloon. Boy, it sure is nice if we could have some kind of mathematical notation that would kind of like just take all them darn words and just make it into one nice, neat little name right there. Rate of change of the volume of the balloon. I do believe somebody once told me that would be shown as dV dt. That'd be the rate of change of that balloon. There we go. Well, to get dV dt, we need to start maybe with an equation that's got a V in it. Wonder where one might be. Oh, look at there, right there. There it is. This is part B. We'll take V is equal to, shoot, I was just jawing there. The people knew that, and I got to go back up here and look, make sure I'm getting the right equation. 4/3 pi r cubed. 4/3 pi r cubed. Okay, now to get dV dt, what am I going to do? Well, I'm going to take the derivative with respect to time. Watch me go. dt of the whole shooting match. Yep, I'll take the left side. You do the right side. Ha, I got you, didn't I? All right, dV dt equal to, now ddt, now don't freak out on me. All it is just power rule on the right-hand side. And this 4/3 pi, that's just a constant. All right, you're going to like it. 4/3 times 3, well, that's going to be 4. It's going to be 4 pi. 4 pi r. Don't forget, got to reduce that exponent by 1, 4 pi r squared. Now you're not done yet. Chain rule, because you're doing d dt, and your variable is r. So you got to multiply by derivative of the inside function, which is r, is going to be dr dt. Now you're done. Okay, now you got to figure out, what are we looking for? We're looking for dv dt. So we got to know r, and we got to know dr dt. I sure hope we got that somewhere. So I'm going back up here looking. I'm looking. Looking. Well, golly, you know that dr dt, I could also call that r prime, right? Yeah, I could call that r prime. Now that's going to be, I want to find r prime when t equals 5. So I'm really looking for r prime at 5. Huh, wonder where that might be. Oh, look, it's in the table. R prime at 5, already seen it. It's my 2.0. There it is. So I'm bringing that down. 2.0, that was my GPA back in high school. 2.0 times 4 pi. Ooh, what's the radius? Huh, radius one time is 5. Radius of the balloon one time is 5 is 30. There it is right there. So I'm just going to, don't forget, you got to square that bad boy right there. That's going to be equal to dv dt. Am I done? No. Got to go back here and look. Find, indicate units, O measure. Well, for Pete's sake, it's the volume, and the volume is changing over time. Well, what are my units of volume? Cubic somethings, what are they? Cubic feetses, all right? Once knew a girl had cubic feet. All right, so we got feet, cube. Now I got to see what's my unit of time. Unit of time looks like it's going to be, where you at there, T? T is measured in minutes. Got it. Cubic feet per minute. All right. I think I'm all done with B. I'm about halfway done. Maybe I might be a little farther. All right, part C. Part C, here we go. Use a right, I love a right Riemann sum. I gotta tell y'all, use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate definite integral 0 to 12 r prime of t dt using correct units. Explain the meaning of that there definite integral in terms of radius of the balloon. Oh, tell you I like this. I'm going right back up to that table. Right Riemann, right Riemann, right Riemann. Riemann, gonna go right style. So 5 subintervals. I hope they busted this table up. Looks good. So I'm looking right here. I'm just gonna show there. This is gonna be my dt. So this is gonna be my change here. That's gonna be 2. Looking for the change. 2 to 5, that's 3. 5 to 7, that looks like 2 again. 7 to 11, that's 4. 11 to 12, that there's 1. Okay, now don't screw this up. I want to get a right Riemann. So what I want to do right now is each one of these y values, or my r prime of t values, I want to circle the right one for each interval. So here I go, circling the right one. 1, 2, 3, 4, 5. Always going on the right side. Not a left Riemann, not a midpoint Riemann. Ain't no trap sum. All right. So now I just got to take the 2 times that. So booda boom, booda boom. Got it? So here I go down below. 2 times 4.0. Plus the next one. Get my change. 3 times 2.0. 3 times 2.0. Shoot, this is easy. And then we got 2 times 1.2. Next up, we got what we're looking at, 4 times 0.6. Last but not least, what do we got? We got 1 times 0.5. 1 times 0.5. Carol Baskin could even multiply that out. 1 times 0.5. All right? Okay. You know right there, folks, that's all you need to do for your right Riemann sum. That there's a numeric answer. That'll get you the Riemann sum point right there too. I guarantee. All right, right Riemann sum using correct units. Well, shoot, what are them units going to be? Think about it. I'm doing feet per minute times minutes. What's that going to leave me? That's going to leave me feet. So I'm just going to put in feet. And that right there, that definite integral from 0 to 12 r prime of t dt, just want to make sure I'm phrasing this right. Explain the meaning of that in terms of the radius of the balloon. So that is going to represent the change in the radius of the balloon the spherical balloon, spherical object resting in the highway. Changing the radius of the balloon in feet from time t equals 0, t equals 12. Right there, there you go, campers. All right, moving on, here we go. Part D, D and we're done. D and we're done. Done for D. I can go feed me some tigers. Is your approximation part C greater than or less than the actual definite integral? Give a reason for your answer. Well, wonder, I'm looking at this. I'm seeing R prime kind of doing this. And I see that what's R prime doing over time? It goes from 0 down, starts at 5.7, goes down to 0.5. They also tell me I gotta make sure of this too, that R radius is modeled by a twice differentiable function of R of time t. So I know it's continuous, and I know what my R prime at t is decreasing. So I'm going to say, check it out. If my function is decreasing, again, it don't matter if I do it decreasing like this or if I do it decreasing, that'd be increasing. You dumb bitch. You got one Carol Baskin on you there. Hang on. It's going to be decreasing, or it could be decreasing like this. But again, I'm doing a what kind of Riemann sum? It's a right Riemann sum. So I just draw one of these in here. There'd be a right Riemann sum. Well, it looks to me, this part here is going to represent, it's going to be an underestimate of what my actual was. So my approximation is going to be less than. So I'm just going to say this. The approximation in part C is less than that definite integral 0 to 12 R prime of t dt. Because what? R prime of t is decreasing on the interval. And that's from 0, 12, put a little t right in between there. There we go. Boys, I hope that helped you a lot. And I sure appreciate it. Come on out and see me in my greater GW Wynnewood Exotic Tiger land. And I just want to say hi, everybody. And I just hope y'all doing well. And happy April Fool's Day. Y'all take care.